good afternoon, and welcome to another lecture on fundamentals of light propagation and scattering. And today we have our 9th lecture. So it was a beautiful day today outside. I hope you enjoyed parts of it, and to make lecture faster so that we can enjoy a few minutes more. Let's try to make it without a break today, okay? And if you're watching the recording, this is obviously not a problem for you. So today we're gonna have a pretty entertaining lecture. I hope we're not gonna have a lot of equations and formulas, just a few to give you a rigorous understanding of the subject, and the rest is gonna be mostly entertaining pictures. So to remind you, the last time we talked about, in last two lectures, we've been talking about waveguide modes and the phenomenon of waveguiding in different structures. And in particular, the last week we talked about the phenomena of surface waves, excitations, localized excitations that exist on a surface between two different media and can propagate along that surface in particular cases. So let's make a break today from waveguides and talk about butterflies. And I don't mean butterflies that we can see here in our region, but some tropical butterflies with these fancy, vivid colors with very bright wings. So take a guess, take a few seconds and make a guess. Tell me, where do these colors of their wings come from? Just taking a random guess. Is it a pigment? Is it an organic dye? Maybe this is something else, an anti-reflection coating that works due to destructive interference. Just make any guess. And Georgi, if you know, don't tell me because I don't want to spoil the surprise. So I hope you made some guess. And here's the reveal. These are two electron microscopy images of two different wings of two different butterflies. And you can see a highly sophisticated and organized structure. And this is the structures, a typical structure that gives colors to butterflies. So it's not a pigment, it's not some dye, it's not even anti-reflection coating. It's a highly complicated and sophisticated structure. And the common feature of these two structures is that they are periodic. This structure is periodic in this direction and in this direction, and this structure is also periodic, almost periodic in the vertical direction and periodic in this direction. And any such structure that has at least one periodicity in the broader context is referred to in nanophotonics as a photonic crystal. And today we're gonna look at fundamental properties of various photonic crystals and their applications. So a lot of pictures that you're going to see today have been adopted from this amazing book by Janopoulos and company, a book devoted to photonic crystals only. This is almost a Bible of photonic crystals. You can have an answer to any question related to photonic crystals in this book. And a lot of what I will be talking today, what I will be presenting today, is based on the content that can be found in this book. So if you want to know the subject a bit deeper, then I can highly recommend you this literature. And this gives you an idea where you can find the answer to any particular question that you might have, where in the book, in which chapter you should be looking for, whether it's a question about infinite, truly periodic structures, or some photonic crystal waveguides that have only one periodic dimension, or it's photonic crystal cavity, or it's a photonic crystal fiber. Okay, so let's start with the basics, with the fundamentals. A photonic crystal is an optical electromagnetic structure that is periodic, at least in one dimension. So let's say our structure is characterized by permittivity epsilon, which is a function of R, and it is periodic if for any combination of a number of lattice vectors, A1, A2, A3, the epsilon repeats itself over and over and over again, no matter how many times we make a jump by this vector Rn, which defines the step in which we can jump, which defines the unit cell epsilon, permittivity of our structure, will repeat itself indefinitely. And these three sketches demonstrate three different possibilities that we can have. We can have periodicity only in one dimension and translational invariance in other two directions. We can have periodicity in two directions or periodicity in three directions. And that will give you one-dimensional, two-dimensional, three-dimensional photonic crystals. And these vectors, A1, A2, A3, they have a special name. They're called primitive lattice vectors. And you may be familiar with this terminology from quantum mechanics or from solid-state physics classes. But we'll come back to that analogy between solid-state and electromagnetics a bit later. And any combination, any integer combination of these primitive vectors gives you some Rn, which defines this jump in the space, and any such jump lands you on a different point in space, but where the structure is essentially the same with permittivity and permeability. If the medium is magnetic, it repeats itself over and over again. So now we can switch from our usual space where we describe the position in the real Euclidean space to something called the reciprocal space. And that is done by the spatial Fourier transform. And this gives us the access to the reciprocal space. This is the space of the wave vectors K, Kx, Ky, Kz. And so we can characterize the system in this space of the wave vectors. This is the same transform, same kind of transform as the one we do when we transform from temporal dependencies to frequency dependencies. So these are kind of spatial frequencies. And what we can do is, if we have these three primitive lattice vectors, we can define three reciprocal primitive vectors, G1, G2, G3, and here V is the volume of the primitive unit cell. And these vectors, they define the Beryllium Zone, which is a very important concept in periodic systems, in electronic periodic systems, and in electromagnetic periodic systems, in any wave periodic systems in general. So what is the Beryllium Zone? Beryllium Zone is the set of all points in the reciprocal space that are closer to the origin of the reciprocal lattice, let's say to the center of the reciprocal lattice, which is usually denoted by the Greek capital gamma. That's any other reciprocal lattice point. So we have a set of gamma points. This guy, this guy, this guy, this guy, this, and so on and so forth. And what this Beryllium Zone is that a set of all points inside here, all these points are the closest to this particular gamma, okay? And that gives you the Beryllium Zone. And this is a very important concept when we analyze the properties of a periodic system. Now, how do we actually find waves that can propagate in periodic systems? We need some general statements that would tell us that the modes, eigenmodes of any given periodic system behave like this, because what we want to find in the end, we want to find a spectrum of some propagating solutions, or localized solutions, or waveguide modes, or whatever we are looking for. And we would like to know some mathematical statements that give us a hint of how that particular solution behaves. And the most fundamental statement about periodic systems is the so-called Blocks Theorem, which again you might be familiar with from quantum mechanics or solid-state physics. And the Blocks Theorem states that stationary solutions of a periodic electromagnetic systems are so-called Blocks waves, where the Block wave is essentially a combination of the usual time oscillating factor, then the lane wave factor, where beta is called it's not the usual wave vector, we'll be calling it Block's momentum, quasi-momentum. And some another function u, where U is periodic function with the period matching our lattice. So if this is our lattice, let's say this is a set of films, okay? And this is lattice A, this is B, this is A, this is B, and the thickness of the entire lattice is L. Then U X plus L equals U of X. So the periodicity of this block prefactor matches periodicity of our structure. So this beta, it is similar to the ordinary wave vector, but it's not a wave vector. It's called a quasi-wave vector. So one of the properties of this U is that it is defined up to addition of any reciprocal lattice vector Gm, where Gm is any integer combination of the reciprocal lattice vectors. So it is M1 J1 plus M2 J2 for three-dimensional periodic system plus M3 G3. Okay, where M1, M2, M3 are integers. And to see that clearly, let us actually take our initial block state, and let's add any combination, arbitrary integer combination of reciprocal lattice vectors to beta. So this is what we get. We have our initial block wave times this new thing. Okay, let's group this new factor with our periodic function U. This is what we're going to get. Now we can forget about this, but this new factor, which appears in brackets here, it is just a new another periodic function matching the same periodicity of the lattice, because U matches this periodicity. But you can verify that this exponential factor is also matches the same periodicity with L, because this is just how these G's are defined. So this is just another periodic function with the same period and the same block wave. So you see that by shifting the block vector, block momentum, by any reciprocal lattice vector, we don't change anything, and solution maintains the same periodicity. That means that we can actually shift all the wave vectors, bring them down to the fundamental Beryllium zone, to the region of space in the reciprocal space, where the smallest region of reciprocal space, and all the vectors can be located here, because it doesn't matter if they're here or here, because shifting by any integer combination of reciprocal lattice vectors doesn't change anything. Okay, so what is the physical meaning of this block state? What is it? Is it a plane wave? Is it a combination of plane waves? So let's figure that out by Fourier transforming any block state, an arbitrary block wave. We can expand it into a Fourier series, right? So we can't expand the entire expression to Fourier series because this isn't periodic. It is only U that is periodic. So let's keep this block factor outside, and let's expand U in the Fourier series. And if we do this, we go through this, and finally we obtain this. And this is just a superposition of different spatial harmonics with different reciprocal lattice vectors. That's basically just different plane waves with different momentum, all shifted by the common factor, by the common scalar factor, which originates from the block wave vector of our solution. Okay, so you can think of a block state in periodic system as a superposition of different spatial harmonics, all shifted by the common by the common prefactor. That's the mathematical property of the block state. So I mentioned that there is a certain analogy, and in fact there is a very strong analogy between wave behavior in electronic and electromagnetic system. And the term photonic crystal actually comes from solid state physics, because what is an electronic crystal? This is a periodic arrangement of atoms that form a crystal lattice, and there are electrons traveling through this lattice, and electrons, the wave function of the electron satisfies the Schrödinger equation with the periodic potential. Okay, this thing is periodic, and by plugging that potential into the Schrödinger equation and solving it, we find the energy spectrum of electrons, and that gives us all these insulators, conductors, and so on and so forth, depending on their Fermi energy. And this is a typical crystal. This is a typical mathematical description of a crystal in solid state physics. And that can be translated into optical, into electromagnetic structures by noticing that the Schrödinger equation is actually very similar to the Maxwell's equations, to the Maxwell equation. It has a different form, but it is essentially some quadratic differentiating operator, and also some potential, and the potential here is played by the permittivity or by permeability in magnetic systems. And when that permittivity becomes periodic, our potential also becomes periodic. And then, just like in the case of electronic systems, where wave function of an electron in a crystal becomes a block wave, the photonic field, the electromagnetic field, traveling through a periodic system also becomes a block wave, very similar to an electron in a crystal. And this analogy goes even deeper, and there are many effects that can be translated from the solid state physics that have been known for a long time onto the realm of electromagnetics, and they have been discovered in optical systems. So this is why such structures are called photonic crystals, because they are analogous to crystals. You just replace electrons with light and you get pretty much the same mathematics. Okay? So now let's start considering some concrete examples of photonic crystals. What can be easier than a one-dimensional photonic crystals formed just by a stack of films, of dielectric films? Let's say we have dielectric film 1, dielectric film 2 of thicknesses L1 and L2, and we stack them into a bilayer unit cell, and we repeat this stack of two films over and over and over again. And this gives us a one-dimensional photonic crystal, a dielectric multi-layer photonic crystal, which has a periodicity in one direction. We'll call that direction X. So now, how about finding these block states, these propagating block solutions of a one-dimensional photonic crystal? How are we going to approach this problem? Well, let's recall the Blocks Theorem. The Blocks Theorem gives us a partial answer. It says that inside this periodic system, all eigenmodes of Maxwell's equations should be sought for in this particular form, where U is some periodic function. We don't know what periodic function, is just time periodic with periodicity L. Then this is the usual plane wave factor, which accounts for propagation in the X and Y and Z axis, along the Y and the Z axis, because of course we're going to be interested mostly in this solution propagating perpendicularly to the layers, but the wave can also propagate at some angle with respect to the layers, so we should include this factor too. And there is the block factor, which actually includes the quasi-momentum beta. Okay, so now what we should do is that we need to pick out a single unit cell. We need two consecutive films labeled by n and n plus 1, and let's choose these two. Let's choose these two films. And I need to be very accurate about whether I include or not the interface with the next field. Because what I'm going to do next is that I'm going to apply the transfer matrix formulas to that. And as you remember, when we are using the transfer matrix framework, it is very important if we include an interface to the next field or we don't. And because I want this unit cell to describe only one primitive unit cell of the structure, I don't want any repetitions here. So what I'm going to do is that I'm going to include this interface between n-1 and n, but I'm not gonna include this interface, which sits right next to this field. Okay. Okay. So now we chose a unit cell, and we can directly apply the Blocks theorem to this unit cell. The Blocks theorem tells us that the field here at this point, at this edge of the unit cell, is exactly like, so this is our R0, and this is R0 plus L. The Blocks theorem tells us that electric field at that point is electric field at the previous point times the Block factor, because this U is periodic, it doesn't change. But because we have the Block factor, this field acquires certain phase delay, which is accounted by this scalar term. Okay, this is the relationship between electric field on that side of the unit cell and on the opposite side of the unit cell. Okay, this is something, but we still don't know this field. If only we knew the relationship between electric field here and electric field here, we could in principle try to resolve this equation, and then that would give us access to beta, but we don't. How should we do this? Well, this is where the transfer matrix formulas comes into play. Now we can represent the total electric field in each field as a set of two counter-propagating plane waves. Again, I'm gonna draw my unit cell. So the field here is two plane waves. The field here is also two counter-propagating plane waves with certain amplitudes A and B. I don't care about these amplitudes for now. What I do care, though, is the relationship between the field exactly here and the field exactly here. This is R0, this is R0 plus L. And I can use the transfer matrix method to find this relationship, right? We know how transfer matrix relates the amplitudes of plane waves at in different parts of the system. So what I should do is that I should split this unit cell into 4 elements. I have interface 1, I have the field, I have another interface, and I have another field. So these are 4 elements that's accounted for by these 4 transfer matrices. The interface transfer matrix, the field transfer matrix, another interface, another field, and we stop. We don't include another interface because then it's going to repeat this, and we don't want repetition. That would be incorrect. So we have 4 primitive elements in our system. We multiply these 4 transfer matrices in the correct order, because as you remember, the order in which you multiply transfer matrices is really important, and multiplication of matrices isn't associative. It is associative. It is not. Georgi, help me. Yes. You can't replace matrices. You can't flip them. And this will be our total transfer matrix. Okay, so now let's combine the two approaches, the Blocks approach and the transfer matrix approach. And when we combine the two, we'll see that on the one hand, the relationship between the fields on this side and on this side is given by the transfer matrix, which we do know. We know all the 4 elements of this matrix. But on the other side, it is simply given by this thing because, okay, on the one hand, it is the 2 counter-propagating plane waves, which we know everything about. But on the other hand, another perspective of looking at photonic crystals is this Block state, which has this thing. And we need to equate the two. So this is essentially an eigenvalue problem for the transfer matrix. And the solution to that problem is the following, is that the determinant of this matrix is 0. So this is the characteristic equation of a one-dimensional multi-layer periodic photonic crystal. It doesn't have to be dielectric, doesn't have to be metallic, it can be any arbitrary one-dimensional photonic crystal it can have. Its unit cell can have 2, 3, 10 gazillion of layers, doesn't matter. The moment you have this transfer matrix, the composite transfer matrix of the entire unit cell, which may contain an arbitrary number of layers, that particular moment, that instant you have at your hand the characteristic equation, which you now can solve. And let us solve this equation by resolving it with respect to propagation constant beta, which we are actually looking for. We obtain this elegant expression, which allows us now to study how beta depends on frequency. So vice versa, how frequency depends on beta, because usually beta is plotted along the x-axis of the plot of any dispersion diagram, and frequency is plotted vertically. Okay, so let's study this dispersion, the resulting dispersion for a simplest case of a photonic crystal formed by two layers. One is vacuum, another is dielectric with some refractive index, and this is the ratio between thicknesses. And this is the resulting spectrum of Block's state, where all the wave vectors were compacted to the first Beryllium zone, because this makes visualization more compact, and actually because it's just convenient. So what this plot reveals is that our photonic crystal has a set of propagating modes with different wave vectors, with different quasi-wave vectors, with different frequencies, and it is symmetric with respect to flipping beta to minus beta, and that makes sense because our photonic crystal has a vertical mirror symmetry. But besides this, we also see a couple of very interesting regions within which there are no propagating states whatsoever. In fact, if you calculate propagation constant for these frequencies and for these frequencies, they become imaginary. The propagation constant becomes imaginary. And we have already seen a behavior like this when we studied surface waves previously. We saw that in some regions, which we called a stop band of a surface wave, our propagation constant turned imaginary, indicating the fact that the surface wave cannot propagate any longer. It will decay exponentially along the surface. And the same happens in photonic crystals. This region, which does not contain any propagating solutions, is called the band gap, photonic band gap. And there are no propagating solutions with real wave vectors within this region. Wave vector turns imaginary, telling you that the corresponding Block's state exponentially attenuates as it propagates. So basically doesn't propagate. This is the photonic band gap. What is the physical origin of this band gap? Well, as always in optics, everything can be explained via diffraction or interference, and in this particular case, this phenomenon is explained by interference. So what we have is a multi-layered structure. Its unit cell is composed of two films, and it happens so that within that band gap, when the frequency of light lies within the band gap, each unit cell, each pair of two consecutive layers acts as a Bragg mirror, reflecting light. So the interference works in such a way that any couple of mirrors suppresses transmission and increases reflection. So it works like an anti-reflective coating, right? This is just a Bragg mirror. And when we stack a few Bragg mirrors on top of each other, 5, 10, that completely suppresses transmission, and so light just reflects from the stack, and that means that light basically cannot propagate. When we make this stack of mirrors infinite and truly periodic, there is no more incident light, there is no more transmitted light, there is just certain block state that exists within the entire periodic structure, and that block state, it can propagate, so it will exponentially decay inside the photonic crystal, and that will form a photonic band gap, a region of frequencies with no propagating states within. This is the physical origin of photonic band gap only in the simplest photonic crystal ever, the 1D multi-layer photonic crystal we're gonna look at. While 3 dispersion curves and the dispersion plot, there are 2 solutions of characteristic equation. Well, it's not 3 or 4, it's actually infinitely many solutions. If you continue this vertical axis in this direction, the frequency, you're gonna see, so this is the first band, second band, third band, you're gonna see fourth, fifth, 10th, etc. There are infinitely many bands, nothing limits them. Photonic band gaps become narrower and narrower, but there are many more propagating bands. So there are 2 solutions of characteristic equation. Well, depends on what you mean 2 solutions. There are 2 solutions for each particular beta, or 2 solutions for each particular frequency. As you can see, if we fix any beta, there are many different solutions, because by plugging different frequencies here, and remember that the elements of this transfer matrix, they depend on frequencies. So by fixing beta, we can actually find many frequencies that will satisfy this expression, because the elements of the transfer matrix, they depend on a very complicated way on frequency. These elements are matrix elements of some product of many matrices. There are different exponents, impedances, refractive indexes. So there is very complicated dependence of these matrix elements on frequency. And you can always find many different orthogonal independent solutions to this characteristic equation for fixed beta. I hope that is exactly what you asked. So this is only the physical origin for the simplest type of photonic crystal formed by multi-layers. There are many other different types of 2D, 3D photonic crystals where the phenomenology of Bragg mirror doesn't quite work, but they're still gonna have photonic band gaps, and I'm gonna turn to these scenarios in a moment. But before that, let's see what happens when we make photonic crystal finite, when we truncate an infinite truly periodic structure. Let's say our structure has, I know, n layers, and it has a left side, right side. We are incident from the left side, and we are interested in reflection and transmission. Well, we can easily calculate the structure, again, using our beloved transfer matrix formalism. We can calculate reflection transmission. This is a very simple exercise, and we're gonna see, if we calculate reflection, that as long as we are outside the band gap at low frequencies, reflection goes back and forth, it oscillates, but then just the moments when we hit the band gap of our photonic crystal, reflection goes to near unity. This is near 1 reflection. And that makes sense in the context of what we just discussed on the previous slide, because now the entire photonic crystal starts to work as a very large Bragg reflector formed by many individual Bragg mirrors. And so the entire thing just reflects all the incident radiation almost ideally, giving rise to near unity reflection. Then, as we increase frequency more, we leave the first band gap, then reflection oscillates back and forth again, and then we go into the second band gap, where reflection is near unity again, and then we go to the third band gap, where we hit another almost flat bands of near unity reflection, and so on and so forth. And you're going to see these alternations between non-zero, between close to zero reflection and near unity reflection as you vary the frequency of the incident field. So yeah, band gaps of periodic crystals, when we truncate them, they manifest as regions of near unity reflection. And this is in accordance with the behavior of a single unit cell, which acts as a Bragg mirror. Okay, let's now increase the complexity of the system, and let's increase the number of dimensions in which the system is periodic. One-dimensional photonic crystal was periodic only in one direction, along the x-axis. In two remaining dimensions, y and z, it had continuous translational invariance. Let's make a system. Let's look at systems which are periodic at least in two dimensions or in all three dimensions. These are typical examples. You can have an array, a periodic array of infinitely long rods, which are continuously invariant along the z-axis, but only periodically invariant along x and y. Or you can have a truly three-dimensional photonic crystal formed by an array of spheres, spheroids, ellipsoids, or even more complicated scenarios. And in principle, all such structures, whether it's 2D, 3D, they feature qualitatively similar spectra with zones, with band gaps separating different zones. And when we truncate these photonic crystals, within the band gaps, they work as near perfect reflectors. So when we're dealing with 2D or 3D photonic crystals, what we want to find is also what we often are interested in is the block wave vector beta. But because the system now has 2 or 3 periodic dimensions, the beta also becomes a vector. It's not just a scalar, it's a vector which has 3 components. Beta, let's label it as beta x, beta y, beta z. These are the 3 Euclidean Cartesian components of the block quasi-momentum. And it becomes a pain to just visualize the dependence of frequency on 3 components of a vector. So what people often do is the following. They consider the Beryllium Zone of our photonic crystal, which can have different shapes. For example, for this particular shape, it is going to be just a cube. For this, the Beryllium Zone is going to be just a square on the plane. The Beryllium Zone is 2-dimensional. Here it's 3-dimensional. For some structures, it is more complicated. Sometimes it's some platonic shape, sometimes it's not. It can be complicated. But what people do in order to simplify visualization is that they choose a set of very special points on the surface of the Beryllium Zone. These are called high symmetry points. And they are often notated, in fact, they're always notated with capital symbols. Gamma, X, M, K, X, U, V, W, so on and so forth. And these points are located in very, very special places of our Beryllium Zone that have high symmetry. These are usually the center. Gamma is always the center of the Beryllium Zone, if it has a center, of course. Then there are vertices, centers of edges, center of this edge, center of that edge, centers of the faces, center of that face, center of that face, and so on and so forth. And what we do is that we project the entire isofrequency onto the entire dispersion on this path. Okay, for example, something like this. And now this is just a linear path, and what we can do is that we can plot frequency as always along the y-axis of the plot, and on the x-axis, instead of just some Cartesian components of beta, we plot this path. So this is our gamma, this is L point, this is U point, X, W, and then we go back to our gamma. So this is a closed loop. And we can have, in this direction, we can go along a different path. For example, we can make K or something else. And then the dispersion diagram becomes just a set of lines. And typically in complicated 3D systems, there are many, many lines, and we're going to see examples just in a second. So this is how dispersion of block states is visualized in the case of higher dimensional photonic crystals. It's not just dispersion diagram that shows you all possible solutions, all possible block states, but it is a projection of the isofrequency on this linear path containing very special high symmetry points that are typically of interest to researchers. Okay, let's look at some practical examples. This is a 2D photonic crystal formed by a rectangular array of dielectric rods placed in a square lattice. This is the Beryllium Zone, gamma point, X point, M point, and this is the path, gamma, XM, gamma, gamma, X, M, gamma. And this is the projection of either frequencies onto this linear path. There are two types of modes, TM and TE. Transverse electric, as always, have electric field. Electric field, I believe in transverse electric, it should be perpendicular to the z-axis. And in transverse magnetic mode is perpendicular to the z-axis, if I remember correctly. And as you can see, their dispersion is quite different. And yeah, one common feature that is common for nearly all dielectric photonic crystals is that the modes, they typically start from the gamma point, they originate from the gamma point, and then they go with near linear dispersion, but then these dispersions, they bend, and at high frequencies, they start to display very complicated behavior. And the fact that dispersion starts linearly from the gamma point makes sense, because at low frequencies, your wavelength is huge. And when the wavelength is huge, that means that the entire wave, the electromagnetic field, sees your photonic crystal, your arrangement of inclusions of periodic dielectric elements as some effective medium. And when a medium is effective, it means it's homogeneous. And so the wave sees the entire photonic crystal as one homogeneous medium, and it propagates through the entire photonic crystal as a plane wave. It doesn't notice each individual element. It propagates like through free space with some refractive index, which is given by the basically average refractive index of the host medium and your inclusions. And this is why we typically will see linear dispersion originating from the gamma points at low frequencies. But of course, when frequency becomes comparable to the unit cell, to the characteristic size of the photonic crystal, that changes, and we start to see some non-trivial behavior. So notice here that it looks like TM modes, they do feature a band gap, a region of frequencies where there are no propagating modes for any wave vector. But TE mode, transverse electric, they do not feature a complete band gap. For any frequency, you can always find a solution with some beta that will be propagating. So this we call a partial band gap, when there is a band gap only for one polarization or for some particular region of the Beryllium Zone. For example, for this region, you have band gap for both polarizations. So this is another example of 3D photonic crystal, and as you can see, this is a mess. This is I believe, so what is this lattice called? Is it the FCC lattice? I think it's FCC lattice, standing for phased cubic centered lattice. And this is the an array of closely packed spheres. This is the closest how you can pack them with a certain filling factor. And when you pack these dielectric spheres, the closest you can, this gives rise to FCC lattice. And this is the typical dispersion diagram of the FCC lattice of dielectric spheres. And like I said, this is a mess. Again, dispersions originate with a linear law from the gamma points, but then it's a mess. And what you can see here is that there is no complete band gap. It's missing. There are some partial gaps, but there is no complete gap. And this is true for most of the photonic crystals. It is very difficult to find a system with a complete band gap, but it is possible. And let us actually look at examples of photonic crystals that do feature complete band gaps. One example is given by the so-called wood pile structure. It's like a periodic arrangement of logs. That's why wood pile logs arranged in one direction, then layer of perpendicular logs, and so on and so forth. And these logs are typically dielectric. And it was proposed independently in two papers by Ho and by Sauser and Dowling in 94, and this is the band gap, the band structure of the wood pile dielectric photonic crystal, featuring a complete gap with no propagating states within this gap. Another example is the so-called inverse opal structure. So what you need to do in order to obtain an inverse opal structure is that you need to take spheres, place them in a periodic lattice. I don't quite remember how exactly you need to arrange the spheres. It may be FCC, maybe something else, maybe BCC, which is another periodic arrangement of spheres. But then, doesn't really matter. You fill the gaps between the spheres with the material, with some dielectric material. You fill the gaps, and then you take the spheres away. Experimentally, you can dissolve the spheres, or if it's some polymer or some organic, or you can etch them away with some chemistry. And then you are left with this structure where you only have the gaps between the spheres which existed previously. And it is called inverse opal. This is a 3D photonic crystal, again proposed by Sauser in 92. And this is the band structure of a dielectric of a typical inverse opal. And there are many, many bands. There is the first band, second, third, fourth, etc. And somewhere here, high above, you have a complete photonic band gap between 6th and 7th bands, or 7th and 8th bands. So the point is, there are complete photonic band gaps in some structures, but they require quite a lot of engineering and knowledge of light propagation. But turns out that photonic band gaps occur not only in highly sophisticated engineered structure, they occur in nature. Let's go back to butterflies that we considered in our first slide. So this is another butterfly. C. ruby is her Latin name, which has bright, vivid green wings. And people have studied that particular butterfly. They took microscopic images, electronic microscopic images of their wings, and they saw under the microscope a structure like this, which is clearly periodic, and it's quite complicated. It looks like some spirals, some helices that are arranged in a periodic structure. And the structure depicted here actually has a name. It is strikingly similar to what's called a geroid. And this is a very sophisticated geometric structure that is periodic. It is periodic in 3 dimensions. It is described by a very complicated space group. I don't even remember the name of that space group. And essentially, it is a series of tunnels which you can traverse in different directions, a series of connected tunnels with junctions. You can go here, you can go here. Okay, and this is periodic. This is one unit cell of that structure. And if you fill these tunnels, these channels with a dielectric material and calculate the band structure, you'll see that it features a complete band gap. So butterflies on their wings have photonic crystals with complete band gaps. And this is where they get their colors from. So evolution, nature, in its course of evolution, has created some structures, very complicated, very symmetric structures that not only are photonic crystals, but they also feature some very special properties, such as complete band gaps. And if that doesn't blow your mind, I don't know really what will. And complete band gaps, they have they allow you to do very interesting things. So this is one example that I like. Here people have engineered a 3D photonic crystal with a complete band gap based on the wood pile structure. And then what they did is that they started removing certain elements of the structure by drilling, by etching, and they started making channels. This is one example of a channel. So this is the region of the initial photonic crystal where they removed the material. And inside the channel, light can freely propagate. And so if you have an input, an output, you can shine with light. On this side, the light will propagate through that channel. It's not going to propagate anywhere else at that particular frequency because the photonic crystal has a complete band gap. The light simply cannot propagate anywhere else. So it is forced to flow in one direction until it reaches the output and it radiates from the output outside. And then the others started doing even more complicated things. They started to drill many channels inside. They started making different terms, junctions, and they observed indeed that light does propagate through this channel. It goes via junctions and it reaches both outputs of the system. And so this is quite interesting demonstration of what you can do when you have at your disposal structure with a complete band gap, and that allows you to channel light in any way basically you want by allowing it to flow through the channel and not allowing to go anywhere else. Okay, so that's about it with respect to true photonic crystals, which do have periodicity, at least in 1, 2, 3 dimensions. And if it is periodic only in one dimension, then it is translationally invariant in the remaining 2 directions. But what we can do now is that we can make a defect in the photonic crystal. Let us consider the original 1D photonic crystal. And now let's remove one layer and insert a defect here. It can be, we can just remove a single film. We can replace this film with something else, with a material of a different refractive index, or we can change the thickness of that particular film. No matter what we do, that completely breaks the periodicity of the photonic crystal. So a photonic crystal is no longer periodic in this direction. Periodicity is broken. And as a result, the Bloch theorem does not apply. It is not valid any longer because it is only valid for truly periodic systems. And so we do not have any Bloch states in this direction. However, if the frequency is located within the band gap, we may have so-called defect states, which are localized around the defect, and they cannot propagate outside, because outside we still have a semi-infinite photonic crystal, and if we are inside the band gap, that photonic crystal, that half of the photonic crystal, will suppress propagation here. This is a band gap. The mode is not allowed to propagate here. And the mod, similarly, is not allowed to propagate in this direction. So if the frequency of some particular solution is located within the band gap, we may be lucky enough to find a defect state that is localized at the defect. So these 2 semi-infinite photonic crystals, they start to act simply as mirrors, suppressing propagation in this direction and in this direction. And the defect mode, it can have 0 wave vector in these 2 directions, or it can have non-zero wave vector, in which case it is essentially similar to Fabry-Perot resonator, where 2 mirrors of the Fabry-Perot resonator are replaced with semi-infinite photonic crystals. And the defect mode is essentially analogous, completely analogous to Fabry-Perot resonance formed by 2 metallic mirrors. And this is generally how the defect mode looks like in the dispersion diagram. So if this is frequency, and this is the parallel wave vector, and parallel wave vector means it is parallel to this plane. So this is the components of the wave vector line in the YZ plane, in which the system is still translationally invariant. We did not break that invariance in Y and then Z. And so these are the bulk modes, extended modes of the photonic crystal that propagate from right to left with different wave vector. And within the band gap, inside here, if you're lucky, we may find sometimes a defect mode which will be localized at the defect. And as we vary the in-plane momentum, the frequency of this defect modes will vary, and we can obtain some line that describes the dispersion of that defect mode. Or we can take a different strategy, and instead of removing or perturbing a single layer, we can remove half of the photonic crystal. We can make it only semi-infinite, and that will give us a surface layer. So on this side of the photonic crystal, we simply have free space. We have vacuum here, air. But here we still have the photonic crystal. So now we may find another type of localized solutions, which will be localized on this side because of the presence of the photonic crystal with a bandgap. So the mode cannot propagate this way because of the photonic crystal, because of the bandgap. But for a defect state, for a surface state exists on the surface, the radiation must also be forbidden this way. And one way that can suppress radiation to free space is that if this mode lies below the light line, then electromagnetic field in this region will have a form of an evanescent wave, and that will allow the mode to be perfectly localized on the surface of the photonic crystal, and such solutions are referred to as surface states. So this is essentially very similar to defect states. It's just that on one side of the system, you completely remove the photonic crystal and protection from radiation. Instead of the bandgap, the protection is given by the light line. So when this mode is below the light line, it can be a surface state. And so you need both of these two factors in order to enable a surface state. You need to be located inside the bandgap of this photonic crystal, and you also need to be located below the light line of the environment which you have on this side, whether it's air, glass, or some other dielectric. And also one little feature of this particular example is that the structure is anisotropic in plane. In x, y, it is anisotropic because it is different if I look along the x-axis or if I look at 45 degrees angle. It is different on micro scale, on microscopic scale. And this is why the surface state, the spectrum of surface states, is not a single line, but an entire region occupied by surface states. Because depending on the angle at which my surface states propagates in the xy plane, it can have slightly different frequency because the crystal itself is anisotropic. If I had films, if I had isotropic films here, that would be a single line. But because it's not a film, but in fact a highly anisotropic arrangement of spheres or whatever, this is not a single line. This is an entire region which can exist below the light line within the bandgap of the surrounding photonic crystal. So this leads us to the concept of hierarchy of defects. And let's formulate this hierarchy this way. So we can start by removing an entire semi-space of photonic crystal, a half of photonic crystal. That gives us access to surface states, which we just described on the previous slides. These are surface states that exist below the light line within the bandgap of the material. But then we don't have to remove an entire half of the photonic crystal. We can remove only a single plane of inclusion, single plane of unit cells. For example, we can remove a single film from a one-dimensional photonic crystal. That will give us access, that will create a linear defect and will give us access to defect modes, which will be characterized by some two-dimensional wave vector, because the system will be periodic or translationally invariant in at least two dimensions, and the resulting states that appear at that defect, they will be characterized by two components of the wave vector. But then what we can do is that we can remove only a single row of inclusions. That's not possible in one-dimensional crystals, because in crystals we remove an entire plane, we have to remove a film. But in 2D crystals, we can remove only a single cylinder, a single rod, And again, that will give rise to another series, another multitude of defect modes, but now they will be characterized only by single scalar components of the wave vector, because the system will be translation invariant only in this direction. We break translational invariance along y and along x, and the resulting defect mode can only propagate this way. It can stand still, it can have zero wave vector, or it can propagate along that defect, which, for example, can be represented by missing rod or by slightly enlarged rod. There will be defect propagating along this defect. And finally, if we are dealing with a truly three-dimensional photonic crystal, we can remove only single site, single inclusion. So imagine if that was a 3D crystal formed by spheres. We can remove a single sphere from here. Now the system lacks any periodicity. It is not periodical on X, Y, or Z, and so Blocks theorem is not valid at all. And as a result, the system doesn't support any block states, but what it can support is that it can support certain resonance residing exactly at the site and perfectly localized in all three dimensions, because it simply cannot propagate anywhere else, because around it is a photonic crystal with a complete band gap, and this wave cannot propagate in any direction or with any polarization because propagation is forbidden. And so if you match your frequency to the band gap of the surrounding photonic crystal, you can find a perfectly localized defect state residing at the inclusion with perfect localization. Another opportunity arises if instead of infinite periodic crystal, we start with a slab, for example, a dielectric slab, and on top of that slab, we impose a periodic potential, a periodic lattice of inclusions or holes or any unit cells. And that gives us what's called a photonic crystal slab. So it used to be just a film with resonances above the light line and waveguide modes below the light line, which we studied 2 weeks ago. But now the system is periodic in X and Y directions. So what's going to happen is that this system will contain a spectrum of guided block states below the light line, which will be block states because of the periodicity. However, these guided modes, they cannot be protected by the bandgap any longer, because on both sides of the system you have free space. You have air on this side, and you have air or homogeneous dielectric on this side. And in order to enable this evanescent behavior on this side and on this side, the wave, the solution, must be below the light line. It must be protected by the light line on both sides of the system. And so the band gap of this structure doesn't play any role in localization here. And this is a typical, again, very typical dispersion of some generic photonic crystal slab. So you have the light line, and you have a continuous of radiating solutions here. Recall our first lecture on waveguides, where we studied what these bound and radiating regions are. So we cannot have, generally, we cannot have any radiating modes, any guided modes here. And all guided modes will be located here below the light line, where they are protected from radiation into the environment. And again, because this particular example that I draw is anisotropic, because propagation in this direction and in this direction is different, the frequencies or wave vectors will be different. And that is why the guided modes of a photonic crystal slab will occupy an entire region. However, there are exclusions, there are very rare exclusions, exceptions to this rule, where we can find a guided mode above the light line. And this is a very rare and exotic case, which is called a bound state in a continuum, because this is a bound state and it is located above the light line in a continuum. So sometimes you'll find certain isolated points which are often located in the gamma point of the Beryllium Zone with 0 wave vector, but sometimes occasionally they're located here. It is not a continuous solution. It is always a discrete set of points which are located in the continuum. Hence the name, bound state in the continuum. These are peaks that you may be familiar with. And these peaks, they typically appear for one of the two reasons. Either there is an ideal destructive interference between radiation going into the surrounding medium, and when this interference becomes ideally destructive, there is no radiation, the mode doesn't carry energy away from the resonator, it becomes ideally confined to the slab, and it can exist with infinite lifetime above the light line. Or another potential reason for existence of a bound state is a symmetry mismatch between the electromagnetic field of the solution and the symmetry of the field in the environment. These are so-called symmetry protected bound states. We're going to talk about bound states in much more details in the next semester. For now, you should just remember that sometimes modes, proper modes, bound modes of periodic structures can be found above the light line, but this is an exception to the rule. So what else we can do is that we could remove only a single site, a single inclusion, single unit cell from the photonic crystal cavity, and again, that breaks the periodicity of the system in all three directions, leaving us with no block states. Block theorem is not valid any longer again. And what we can find in this case are localized solutions that reside at the defect, that are concentrated, focused on the defect. But this time, the photonic crystal, surrounding photonic crystal, doesn't completely protect us. Because in the case of 3D photonic crystals, when we remove a single defect, that solution is ideally protected by the complete bandgap of the surrounding crystal. Now, bandgap protects us only from radiation to the sides. We cannot radiate here, we cannot radiate here, but we still can radiate to the environment because the light line doesn't protect us. The light line protects from radiation only modes that are characterized by some periodicity or by some block momentum. These modes, it's not periodic, it is localized. So if you do a Fourier transform of this field, you're going to obtain all different wave vectors. And these components, these Fourier components, they will easily radiate to the environment. The light line does not protect from radiation. And so this solution, this solution of Maxwell's equations will have only finite lifetime. This is a resonance. This is so-called photonic crystal cavity modes with finite lifetime because of leakage to the environment, because the photonic crystal doesn't protect from that leakage. And this is usually how these photonic crystal cavities are engineered. So we have an ideal periodic two-dimensional lattice imposed on top of some metallic or dielectric membrane or field. Then we remove a number of inclusions. Usually it's 1, 2, 3, 5 people particularly like to remove an odd number of inclusions for some mysterious reason. And then we also play with these inclusions a little bit. We slightly shift the two edge holes, and we also can slightly change the radius, and we obtain a localized solution that sits at our defect and only slightly radiates to the environment. And despite that mechanism of leakage to the environment, the Q factors of these cavities are surprisingly high. These are one of the best resonators that exist in that exist with current fabrication methods. And Q factors of these cavities typically range from hundreds to millions. These are one of the highest Qs that you can make with existing fabrication techniques. What else we can do? Well, I suppose we can do this. Instead of removing only a single defect from photonic crystal slab, we can remove an entire row. And again, let's recall our hierarchy of defects. We can remove a semi-space, we can remove a single plane, or we can remove a single row. And let's apply this hierarchy in this particular case. So we remove this row, and now the light can travel across this, along this channel, and this time it will be completely protected from radiation, because the photonic crystal on this side and on this side protects us from radiation here, but also the light line, this mode is below the light line, and it's an ideal block state. It does have block form in this direction, so it's a single wave vector, and if that mode lies below the light line, it will be protected from radiation. So this is in fact a perfect waveguide mode that propagates along the given direction, and it is protected by the light line and by the surrounding bandgap of the photonic crystal at the same time. Okay, one, I think, final opportunity is 1D waveguides. Instead of starting with the slab, let's start with the waveguides with finite cross section. Let's say this is something with rectangular cross section. Okay, and an example of a system like this that we considered two weeks ago was a dielectric circular cylinder waveguide. And you remember that it supports a spectrum of guided modes below the light line. But now what we do is that we cut this waveguide and we impose some periodic potential. For example, we can make a series of holes here. We can drill periodic lattice of holes, so we can just completely remove certain elements and even make this waveguide turn it into a series of disjointed pieces that are not joined together any longer. However, the system is still periodic. It is periodic along the x-axis, and therefore the Blocks theorem applies. And we can try to find solutions, localized solutions of the system below the light line. Then the light line will protect us from radiation to the environment. Okay, and we can find a spectrum of waveguide modes that propagates along such a crystal, such a 1D linear crystal. And one very common practical implementation of such 1D photonic crystal waveguides is the so-called coupled resonator optical waveguide, or abbreviated as CROW. So this is just a bunch of resonators, bunch of disks, very often, or micro rings, coupled together, placed certain distance from each other, typically at a sub-wavelength distance. And the way it guides light through the system is that these two resonators, they talk to each other, and light from one resonator jumps to another, to neighboring resonator, and so on and so forth. And despite the fact that they are not joined together, this is not a single piece of material, as soon as the mode is located below the light line, you cannot radiate to the environment. This may seem surprising, but as soon as the frequency and wave vector of the mode is somewhere below the light line, it will be protected from radiation by the Blocks theorem, by the light line, and you're not going to have any radiation. And sometimes such waveguides, they become quite efficient. Yeah, so this is the typical dispersion diagram of a 1D linear waveguide, where we have a certain spectrum of guided modes below the light line. What is important here is that for any such periodic system, there always exists an upper limit on the frequency of guided modes. How can I show you that there is an upper limit? Okay, let's say this is our wave vector, this is frequency, and this is the light line. And there is another light line going this way. And let's suppose I can have a guided mode solution above this critical frequency somewhere here, okay? But because this is not a real wave vector, this is Block's wave vector. Remember that Block's wave vector are equivalent with respect to shift by certain amounts, by the reciprocal lattice vector. And so if I shift this guy, it will appear, I think it should appear here. But this is above the light line. And above the light line, radiation is allowed. So this mode, despite that it is seemingly located below the light line and radiation should be forbidden, it is not. Because if we only shift its wave vector by an appropriate amount, by an appropriate number of reciprocal vectors, it goes above the light line. And it clearly shows us that this mode will not be confined to the waveguide and it will radiate. So this is located in the continuum, within the continuum of solutions, within the light cone. And by doing this series of shifts by the reciprocal lattice vector, you can easily see that the upper limit, the upper frequency limit on frequency of truly guided modes is given by this combination. This is simply pi c over L, where L is the periodicity. Above that frequency, you cannot find any truly guided modes. All right, defects. Yeah, one last application of the hierarchy of defects. So we can start now with a photonic crystal waveguide, with 1D photonic crystal waveguide, and perturb or remove a single unit cell. For example, we can remove it, or we can split the periodic lattice in two and move them apart. That again will form a defect, and there will be a defect state localized at a defect. But again, similarly to photonic crystal cavities, because our band gap works only in this direction, leakage outside is not forbidden, it is allowed, and this resonance will have only a finite lifetime, so we are not protected by the light line. This is one practical implementation of such structures. So here we have a perfect dielectric waveguide without any periodicity. This is just a dielectric film and dielectric strip waveguide, and it supports a continuous spectrum of guided modes. Then we start forming a periodic photonic crystal. You see these holes here, 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 here. So this is a truly periodic photonic 1D photonic crystal waveguide. But now we remove a particular defect from here. They removed just one hole, thus creating a 1D photonic crystal defect, and this becomes a cavity. This becomes a microcavity. And what happens with this incident signal, which is propagating via these guided modes of the dielectric strip, is that it is getting partially reflected at the resonance of the microcavity, or sometimes vice versa, transmitted because you have one more transition from the continuous dielectric strip into this area where you have a periodic crystal, then you have the cavity, then you have another area with periodic 1D photonic crystal waveguide, and then you have just a continuous dielectric strip waveguide. And these are the experimentally measured transmissions. Yeah, you can see that at the resonance, you have a maximal near unity transmission with very high Q factors, and that allows us to do, you to do different kinds of filters on the waveguide. Some resonant filters for transmission and reflection. We can implement them inside the waveguide. And one last example of using photonic crystals is given by so-called photonic crystal fibers. So these systems are not periodic in any dimension, but still they are called photonic crystals because they utilize the idea of photonic crystals of periodicity. So what a photonic crystal fiber is that it is a dielectric fiber extending in this direction, and that would work without any. This is a dielectric, this is air, This is a cylindrical dielectric waveguide which has a spectrum of guided modes. So this is just the principle of index guiding, where guided mode propagates below the light line of the environment thanks to the total internal reflection. And that could work without any holes. But now what we do is that we make these holes that go along the cylindrical axis of our fiber. And what it does is that it enriches the waveguide with some very interesting properties. If you remember approximately the dispersion diagram of the dielectric cylindrical waveguides, you remember that it is a mess. There are many different modes at high frequencies. There are TE, TM, some hybrids, HE, EH modes. It is a mess. And that often complicates life. Often we want a system, we want a fiber, a waveguide that is a single mode. And cylindrical waveguide is single modes only at very low frequencies. Above certain frequency, it becomes multi-mode. So one very nice property of such photonic crystal fibers is the so-called endlessly single mode regime. And I cannot explain now how it works. That would require a lot of time. And if you're looking for explanation, there's an excellent explanation in the book. But roughly speaking, the way it works is that the contrast, the effective index contrast between the core and the cladding of the waveguide reduces at high frequencies. It becomes smaller and smaller at shorter wavelength. And when the contrast is small, your waveguide, it wants to be single mode. It cannot be multi-mode. Because when the contrast is small, there is only the fundamental mode that exists in the waveguide. And this is exactly what happens in this kind of photonic crystal fibers. Note that this is the difference between the light line frequency and the real frequency. And in this region, we have only fundamental guided mode. So our guide, our fiber, remains single mode even at very high frequencies. And this is the essence of the endlessly single mode regime. But like I said, this could work without any holes. That would be multi-mode, but it still would be a waveguide, because this is just index guiding. However, there is another opportunity for us to employ photonic crystals in order to enable guiding. And we can sketch this opportunity here. Now, instead of dielectric here, we have air. And without photonic crystal, without this or without this thing couldn't work. Because this is air, this is air. We need some mirrors. And in this approach, the role of the photonic crystal is to work as a mirror. So basically, it replaces metal or perfect electric conductor in early examples that we considered 2 weeks ago. This becomes a mirror. Okay? And you can basically take a one-dimensional photonic crystal that we considered in the first part of today's lecture, and you can wrap it around the cylindrical axis. And that will create a circular mirror that should confine the electromagnetic mode inside. Okay? Or you can take a 2D crystal formed by a hexagonal array of air holes inside the electric matrix, and at some frequencies it will also create a band gap, and this structure will work as a nearly perfect mirror. So these things are not truly periodic. However, in practice, the thickness of this mirror is sufficient for near perfect confinement of electromagnetic field inside in the interior of the waveguide. And to finalize the lecture, I want to present you 2 real-life implementations of photonic crystal fibers. These are not index-guided fibers. So this is air, and that wouldn't work without holes. Okay? And so in this particular example, we have a triangular lattice of air holes in glass matrix. And that layer of, not layer, it's that network, that lattice of holes, of air holes, surprisingly acts as a very, very good mirror confining radiation to the internal region of the waveguide. And another similar example is the just Bragg fiber Bragg fiber thin when we take our 1D photonic crystal formed by two alternating dielectric layers, films, curve it around, wrap it around the cylindrical axis, and form a fiber where this plays the role of a metallic mirror but without metals and confined radiation to the internal part of the waveguide. So that's all for today, guys. Thank you for your attention. So I hope that was entertaining for you. So today we learned the basics of photonic crystals. We learned Blocks Theorem, which gives us the fundamental for mathematical description of electromagnetic fields in periodic systems. We looked at various 1D photonic crystals and discovered the emergence of photonic band gaps. Another important concept from today's class is the hierarchy of defects. Then we looked at photonic crystals, photonic crystal slabs, linear photonic waveguides, and finally photonic crystal fibers. That is it. And next time we switch to radiation. So see you next time, next week.